Hey everybody, Chris McClure here again, and we're going to now review rational expressions, which have to do with these fractions of polynomials. Okay, so what we're talking about here is a fraction where you have a numerator and a denominator that both contain polynomials. Now, just like any good fraction, we need to be able to reduce it, meaning write it so that there aren't any factors common to both the numerator and denominator. So how we do that is we completely factor the numerator. In this example here, we have x squared plus 4x plus 4, which we can factor as x plus 2 times x plus 2. And in the denominator, we can factor that completely as well. We have x squared plus 3x plus 2 being factored as x plus 2 times x plus 1. And then we can then cancel that common factor of x plus 2, leaving us just with x plus 2 over x plus 1, which is now a reduced rational expression. We don't necessarily call it a fraction when it involves polynomials. We call it a rational expression. Okay? So let's do a couple more examples. For this first example at the top, we completely factor that. Remember, that is a difference of cubes. X cubed minus 8 factors as x minus 2 times x squared plus 2x plus 4. In the denominator, we can factor that completely by pulling out an x squared and then times x minus 2, then cancel the x minus 2's, leaving us just with this nice reduced fraction there, or rational expression. Here in the second example, again, the concept is still the same. Completely factor the numerator, completely factor the denominator, cancel that common factor of x minus 4, leaving you with... Now, before I move on, just notice that the 4 minus x and the x minus 4 are negatives of each other. Now, you could take the negative of x minus 4 to give you the 4 minus x, or you could take the negative of x minus of 4 minus x to give you the x minus 4. But either way, you're going to get a negative somewhere in there. So now we're just left with, after you cancel the x minus 4, you're left with the negative 2 over the x plus 3. All right, so that is a nice reduced rational expression. Okay, moving along here. Just like with fractions of numbers, we can add and subtract these rational expressions. Multiplication as well. Now, when we multiply the two rational expressions, you multiply the numerators, multiply the denominators, and then reduce by canceling any factors common to both the numerator and denominator. If you're going to do division, if you're going to take one rational expression divided by another, well, then you'll just invert that denominator and then multiply. Meaning, one rational expression divided by another rational expression is the same as taking the first rational expression times the reciprocal of the bottom rational expression. Okay? So let's go ahead and see some examples here. In this first example here, we've got the product of these two rational expressions. And we can go ahead and multiply the numerators and denominators, but we know that we're going to have to cancel any common factors. So go ahead and factor everything and then identify any common factors. And So notice that the x minus 1 is common to both the numerator and denominator. Notice that the x squared plus 1 is common as well. So you'll cancel those, leaving you with just 4 times the x minus 1. This x minus 1. Notice up here there were 2 factors of x minus 1. One of them got canceled with this guy right there. So leaving you just with this 4 times x minus 1 in the numerator. And in the denominator, we have the x times the x plus 2 right here. So we have this reduced fraction. Now, it's okay for you to leave your final result like that, or you can multiply everything out again. Either way is perfectly fine. Here for the second example, we're doing the division. So like I mentioned before, you'll take the top rational expression times the reciprocal of the bottom rational expression, and then do exactly what we did in part A. Factor everything and cancel common factors. So that's exactly what we're doing here. We're factoring everything, cancel the common factors of x minus 2, for example, canceling x plus 3. And I think that's about it. Okay, hold on. My PowerPoint just decided to choke on me, but luckily this restarted pretty quickly. So I guess I have a touchy machine here. All right, so we just finished this problem here. So we carried out this multiplication for the first example there, and we carried out division in the second example here. Okay. All right, so so we're going to now take a look at adding and subtracting once the PowerPoint comes back up again. Sorry about this, folks. Usually my computer is a lot more reliable than this. That's okay, we'll work beyond it. Because we are resilient. All right, here we go. Now, adding and subtracting rational expressions uses the same rules as for fractions. You basically need a common denominator. And when you have a common denominator, all you need to do is just add or subtract the numerators with that same common denominator. Okay, so let's just review that. Suppose that we've got 2x squared minus 4 over 2x plus 5 plus x plus 3 over 2x plus 5. So we have common denominator, so we just will add the 2x squared minus 4 plus the x plus 3. Add those two numerators. Okay, and then don't forget, as a final step, if you can reduce the final fraction there, then go ahead and reduce it. Meaning factor and look for any common factors. All right? Which in this case, there aren't common factors for you to cancel. So we're done with that example. Now, for part B, we're subtracting. Notice that you have a common denominator of x minus 3. So you simply subtract the numerators. X minus 3x plus 2. Don't forget to surround that second numerator with parentheses. And then you have x minus 3x plus 2. So, and don't forget to, carry out that subtraction for that second term within the parentheses. So you have x minus 3x minus 2. And x minus 3x is negative 2x. So you have negative 2x minus 2 over x minus 3. Now you could factor out a negative 2 in the numerator so that you are doing what you're supposed to be doing in completely factorization, doing the complete factorization, and identifying any common factors, and there aren't any in this case. Now, if you are adding or subtracting fractions where one denominator is the negative of the other denominator, well, you can get the common denominator by multiplying one of the fractions by negative 1 over negative 1. So look at this example here, and we can just multiply that second fraction by negative 1. Look, when you have a difference like 3 minus x, and you want to reverse the direction of that subtraction, meaning turn that 3 minus x into an x minus 3, just multiply it by negative 1. All right, so your 3 minus x will become, x minus 3. Or the negative of x minus 3. That's the same thing as 3 minus x, okay? So if you have 2x over x minus 3 plus 5 over 3 minus x, well, that would be the same thing as 2x over x minus 3 minus 5 over x minus 3. And then you can go ahead and carry out that operation. You have 2x minus 5 over x minus 3. Okay? Moving along here. But if you have rational expressions where the denominators are not the same at all, then you're going to have to do something in order to get the common denominator. So using the same sort of techniques that you would with fractions of numbers. Okay? Moving along here. Now, if you have denominators that are fairly simple, then all you need to do is take the first fraction multiplied by 1 in the form of that second denominator over the second denominator. And then same for that second fraction multiplied by x over 4 plus x plus 4 over x plus 4. So that we have a common denominator of x plus 4 times x minus 2. So here we've got this addition operation, x minus 3 over x plus 4 plus x over x minus 2. Multiply the numerator and denominator of this first fraction by x minus 2 over x minus 2. Remember that you have to multiply by some fraction that's exactly equal to 1, so that we're not changing the value of the original fraction. We're just changing the way that it's expressed so that it has the same denominator as the second fraction, which you're multiplying by x plus 4 over x plus 4. All right, that we're doing here. Remember, this guy is also equal to 1. So now we have two fractions with a common denominator of x plus 2 times x minus 2. And now we can go ahead and add the two numerators together, multiply out the numerator, combine like terms, factor, and cancel any common factors, okay? Moving along here. Here we have another example here. X squared over x squared minus 4 minus 1 over x. So multiply the numerator and denominator of the first fraction by x, and multiply the second fraction by x squared minus 4 over x squared minus 4, like we're doing over here. So you have a common denominator of x times x squared minus 4, and now you can have x times x squared, which is x cubed, minus x squared minus 4. All right, now simplify that numerator here after you multiply everything out, collect like terms. Now, again, practice good math hygiene, factor the numerator and denominator if you can. Cancel any common factors. So reduce as necessary. Now, if you have fractions that you're adding or subtracting, and the denominators are a little bit more complicated, then all you need to do is find the least common multiple of the denominators. In other words, find the LCD for the two fractions. So basically means, instead of multiplying the numerator and denominator of the first fraction by the denominator of the second fraction, and vice versa for the second fraction with respect to the first, then that could give you a very nasty problem in having an overly complicated operation. So all we'll do is we'll just multiply numerators and denominators of both fractions by the most simple expression as needed. Okay, so basically, like I'm saying, is identify the least common multiple of both the denominators, and then multiply each fraction by an appropriate factor. Okay, so this kind of basically gives you a nice little breakdown of what to do. Let's just dive right into an example of finding the least common multiple of two polynomials. Here we've got this polynomial and this polynomial, and luckily they're already factored. All right, we already know how to factor polynomials completely. Now the LCM is going to be a polynomial that has the number of each factor that appears the most from either one of the two polynomials that we see here. So let's go through and identify each factor. First of all, let's look at x. There's one x in the first polynomial, and there aren't any in the second polynomial. So we know the LCM is going to have 1x. Now let's take a look at x minus 1. There's two factors of x minus 1 in the first polynomial, one factor of x minus 1 in the second polynomial. So because the highest number of factors of x minus 1 that appear in either polynomial is 2, then our LCM is going to have two factors of x minus 1. Now let's look at the factor of x plus 1. There's one factor of x plus 1 here, there's 3 over here. Our LCM is going to have 3 factors of x plus 1. Finally, let's take a look at this factor of 4. There's one factor of 4 to the right, none on the left, so our LCM is going to have a 4 as well. So, drum roll, our LCM is going to have to be 4 times x minus 1 squared times x plus 1 cubed. Okay? So there's our LCM there. Alright, so this polynomial right here is a multiple of both this polynomial and this polynomial. And of all the multiples of those two polynomials, this one right here is the smallest. It's the simplest. Okay? So this kind of is the procedure for finding the LCM. So now let's use that skill for adding these two fractions. Now, notice that the fraction on the left, denominator, factors as x plus 2 times x plus 1. For the second fraction, that denominator factors as x minus 1 times x plus 1. So there's the complete factorizations. Now, notice that both of those polynomials from the denominators have a common factor of x plus 1. So in order for us to get an LCM, the first polynomial will also have to have a factor of x minus 1 the second polynomial would have to have a factor of x plus 2. So the LCM is going to have x plus 2 times x plus 1 times x minus 1. So that means for the first fraction, we'll multiply by an x minus 1. That's what's missing here. So we'll multiply numerator and denominator by x minus 1. And then for the second fraction, because it factors as x minus 1 times x plus 1, it's missing an x plus 2. So we'll multiply that second fraction Here's the second fraction here. We'll multiply it by x plus 2 over x plus 2. So we've got now this fraction plus this fraction with the common denominator, and then we can add the numerators now. So adding the numerators of our modified fractions that are now having common multiples, you have x squared minus x plus whatever this is FOILed out on the right. So combine those numerators by multiplying everything out, combining like terms, factoring however you can, canceling in common factors, so that your final result is reduced. Okay? All right. Here's another example of adding two fractions, and in this case we're actually subtracting two fractions. We need to get a common denominator. The denominator here is x times x plus 1. The second fraction has a denominator of x plus 1 squared. So what is going to be the LCM of x times x plus 1 and x plus 1 squared? Well, we need a factor of x as well as two factors of x plus 1 that you see from down here. So our LCM is going to be x times x plus 1 squared. So the first fraction we multiply by another factor of x plus 1 over x plus 1. And then the second fraction multiply by x over x. Okay? So then the problem now involves two fractions with the common denominator. And just like we did with the previous problem, you now multiply out, after you combine the numerators by subtraction, you multiply it out, combine like terms. With this fraction here, try to factor that numerator if you can and reduce the fraction if needed. Our next little topic here involves simplifying complex rational expressions. And no, this does not involve complex numbers, but this means rational expressions where you have rational expressions in the numerator and or the denominator. And there are two different methods that I'm going to show you. The first method involves combining any rational expressions in the numerator into one single rational expression. And same thing for the denominator. And then taking the rational expression in the numerator, divide it by the rational expression in the denominator. Otherwise, for method 2, you can just identify an LCD for all the fractions involved in the numerator and denominator, and multiplying the numerator and denominator of the big fraction by that LCD, and that'll simplify that rational expression. Okay, so let's take a look at both methods. Here's the first method, where we've got this complex rational expression. It's complex because we've got these fractions in the numerator, this fraction in the denominator. So the method 1 tells us to combine these two fractions, add them. All right, so here's what it looks like where we're adding those two fractions. All right, so now you have a single fraction over a single fraction, which means that you take the first fraction, the fraction in the numerator, divided by the second fraction, meaning you multiply by the reciprocal of that fraction in the denominator. So you just took this x plus 3 over 4, flipped upside down, and then multiply to get you this new expression right here. And notice that you can cancel a factor of 2, right? Because this 4 right here factors as 2 times 2, and you have this 2 down here in the denominator, so you cancel those 2's. And leaving you with this reduced final fraction. Again, you don't need to leave your final fraction in factored form. You could multiply it out, so you have 2x plus 12 over x squared plus 3x. And it's perfectly fine for you to leave it in either form, this way or this way. Moving along here. The second method tells us to multiply the numerator and denominator of our complex fraction by the LCD for all of the small fractions involved. So here's the same example as we saw for the first method, but look at all the denominators. There's a denominator of 2, of x, and a 4. So the LCD, meaning the least common multiple of those three numbers, is going to be 4x. So multiply the numerator and denominator of the large fraction by 4x. And when you do that, you multiply 4x times the entire numerator of the big fraction. You have 4x times 1/2, giving you what? Giving you 2x, huh? Okay, because 2's will cancel. Also, you have 4x times 3 over x, right? That's what you did when you used the distributive property in the numerator there. So you have 4x times 3 over x. So the x's will cancel, leaving you with 4 times 3 is 12. So the numerator now becomes 2x plus 12. In the denominator, you multiply that by 4x over here. 4's will cancel, leaving you with x times x plus 3. And leaving you with this fraction here, you can go ahead and factor out another 2 if needed, and then you see you have a completely factorized final fraction. You cannot simplify it anymore, so we're done. Yeah, look, you use either way, whichever is comfortable with you, whatever you're comfortable with. Here's another example where we're going to simplify a complex rational expression. All right. Now, we could combine the numerator fractions here by rewriting this 2 as 2 times x minus 4 over x minus 4. And then the denominator, you could write that 1 as x over x. So we're using that first method to simplify this complex expression here. All right, so that's what we did. We're going to combine these two expressions in the numerator and in the denominator. All right, we're combining them, simplifying them however we can. Now at this point, we're going to then take the numerator times the reciprocal of the denominator. All right, that's what we're doing. Notice now we are going to cancel a common factor of x minus 2, just like we could have done up here as well, leaving us with x plus 4 times x divided by x minus 4, which is as simple as we're going to get it. Okay? All right, let's see what happened here. It looks like PowerPoint froze up on me. I'm going to pause and get this going again. I'll be with you here in a second. Okay, folks, I'm back with you again. Sorry about that. Had a little technical difficulty, but we got PowerPoint recovered. The last thing that I wanted to talk with you about is this application, aka word problem, that illustrates the necessity of using the simplification of rational expression in order to do anything useful with it. Now, here's a picture of an electrical diagram here. Simplified picture of a circuit. This symbol right here shows a battery or some voltage source. In particular, this is a battery. And electricity is going to flow in this direction, meaning the electrons are going to flow in this direction. And then, as they round the corner here, they're going to go both through this resistor and this resistor. A resistor is basically a device that slows down the electrons, kind of like a pinch in a hose. Provides resistance. Not a very interesting circuit, but we're using this just to illustrate a point, though, that says if you got two resistors in parallel here, then you can calculate the combined resistance, meaning the resistance across this point from here to here. What is that overall resistance? Now, suppose that this resistor up here, up top, has a resistance of, R sub 1, measured in ohms. And that the second resistor down here, and the bottom one, has a resistance of R sub 2, ohms. No, meaning, so R1 could be, say, 6 ohms, and R2 could be 10 ohms, whatever. But we could just leave it more general and let the ohms be represented by R1 and R2, and then we can plug in some specific numbers later. Now, there's a rule that tells us how to find the overall resistance across a parallel arrangement of resistors. That says that the overall resistance is going to be 1 over the sum of the reciprocals of those resistances. In other words, 1 over R sub 1 plus 1 over R sub 2. So what we're going to now do is just simplify this. And one way that we could simplify this is by using that second method where we'll multiply the numerator and denominator by R sub 1 over R sub 2, which is, the LCD for these two fractions. So when we do that, in the numerator, of course, we've got R1, R2. In the denominator, when you take R1, R2 times the 1 over R1, the R1s cancel, leaving you with R2 right here. And when you take R1, R2 times the 1 over R2, the R2s cancel, leaving you with R1. So this complicated fraction or expression can be rewritten in this more simplified expression. And now we can go ahead and plug in any particular numbers that we want. So for example, if R sub 1 is 6 and R sub 2 is 10, we can just go ahead and plug in those numbers. So plug in 6 for R sub 1, plug in 10 for R sub 2, and we have 60 over 16, which simplifies to 15/4, which is 3.75 ohms. Did I say volts? I mean ohms. So even though Let me write that down, 3.75. So even though that the one resistor is 6 ohms and the second resistor is 10 ohms, the overall resistance is smaller than either one of those two individual resistors. Okay? Interestingly enough. So now we know how to simplify this complicated rational expression. Okay? Alright, so we're just about done here. Our next video, which I'm going to record on Monday, June 3rd, will involve handling roots and powers. Alright, hopefully all of this stuff is a review for you based on your previous studies, okay? Well, I'll talk with you later. Enjoy the rest of your weekend, and I'll see you on Monday. Okay? I'll keep these annotations. Oops. So let's stop this.